Hi guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to talk about another important unsupervised method, which is called clustering. So clustering is kind of unsupervised learning, so we require data but no labels. So it is useful when we don't know what we are looking for. So the basic idea behind that is we want to group similar data together. So let's say, as an example of clustering, let's say we have some data points in 2D space. We don't have labels, so all of them are like together, are similar together. When you see this kind of data points, probably you could group this data into 1, 2, and 3 groups. Okay, so it is an example of clustering. But so this is one case of clustering, but there is another way to cluster these data points. For example, you could put this data point in one cluster and this one in another cluster. Or another possibility is maybe you want to put these two into one cluster, these two into one cluster, these 4 in one cluster, and something like this. So you don't have a very clear guidance for grouping the instances. And so the question is that, the basic idea is that we want to group similar instances together. So the question is that, what does the similar mean? So one option is using Euclidean distance. So for Euclidean distance, we know that the distance between x and y is now Euclidean distance. So in here we used squared of Euclidean distance. So then we have 2 points in a space that those are close to each other. Then it means that their Euclidean distance is low, so their similarity is high, and vice versa. So if we have 2 far points, then the Euclidean distance is high, so the similarity is a low number. Okay, so clustering results are crucially dependent on measure of similarity. So in here, if instead of Euclidean distance you use another distance like Hamming distance or other kind of distances, then the results of clustering will be totally different, because the clustering results are fully dependent on the measure of the similarity or distance between the points to be clustered. Okay, let's go on. So we could categorize the clustering algorithms into 2 general algorithms. The first one is partition algorithms, and the second one is hierarchical algorithms. And in here we have, for example, Kmeans, which we want to talk about it in this session, and we have mixture of Gaussians, which we will talk about it in the next session. We have spectral clustering, and in here we have two general approaches, bottom-up and top-down. Okay, so today we want to talk about K-means as a clustering algorithm. So maybe you ask yourself, okay, when do we use clustering, or is there any kind of example for real-world application of clustering? The answer is yes, there are a lot. For example, image segmentation is a really classic example of clustering, in which we want to break up the image into meaningful or perceptually similar regions. If you don't know about image segmentation, so let's see. Okay, for example, in here you could see that we have the volume segmentation of a 3D CT scan. So different colors probably assigned to different regions. Maybe you don't know this is what is this, but you know that this is a different region from this region. So it is a classic example of clustering, okay, or this one. This is kind of clustering example. Okay. So how does K-means work? So K-means is an iterative algorithm for clustering, and it works with this algorithm that I write down now. So the first step is initialize. So we pick K. So the K is hyperparameter that the user or you specify at the start of K-means. For example, you want to have just 2 clusters, so you set K to 2. If you want more clusters, you could set it 4 or whatever you want. So K is a hyperparameter of this algorithm. So pick K random points as cluster centers. So this is the initialization. Then the alternate step that we want to iterate over that is a 2-step thing. The first step is that we assign data points to closest cluster center. 2, we change the cluster centers to the average of its assigned points. And actually we stop when no points assignments change. Okay, so what does it mean? So it means that if we have some data like this, so first we pick K random points as cluster center. So let's say we choose 2 for the cluster numbers that we want, and we randomly select here and here as the cluster centers at the beginning. Okay, so assign data points to closest cluster center. Let's move this to here. So this is one random center and the red one is another. Okay, so now we assign data points to closest cluster center. So for example, for this data, this data is based on Euclidean distance. If we calculate the Euclidean distance, the Euclidean distance between these two, between the data points and this cluster point and this cluster center, and this point and this cluster center, this is closer to this cluster center. So we marked it as blue. Okay, so we do this for all of the points. So we assign red to these points and probably blue to these points. Then after assigning, we change the cluster center to the average of its assigned points. So after this assignment, we calculate the average points of these blue points. Then we move the cluster center to somewhere around here, because this is the average point of these blue points. And we do the same thing for the red dots. And we do this iteratively until no point assignment change. Okay, so the algorithm is really simple, and we could see how does it work in here. So first, the green points are randomly pick cluster centers. Then, as you could see here, then nearest data points assigned to the cluster centers. Then cluster centers move to the average points of their clusters. Okay, so after running your algorithm, you will have 4 different clusters. Okay, okay, so now we want to know what properties does Kmeans have. So the first property is that it guaranteed to converge in a finite number of iterations. So it is a good thing that your algorithm converge in finite iterations. And if you want to know about the computational complexity for assigning data points to closest cluster to the closest cluster center, it needs O of kn times, and for changing the cluster center to the average of its assigned points, it needs O of n time complexity. So it is actually a good performance algorithm, because it is linear in number of data. Okay, now the next question is that probably, so in here we use Euclidean distance. Maybe you want to use another distance. So what properties should a distance metric have in general if you want to choose a metric as a distance? So distance properties. The first one is symmetric. So if you want to choose a metric as a distance, that distance should be symmetric. it means that D of A and B should be equal to the D of B and A. Why? Because otherwise we can say A looks like B, but B does not look like A. Okay, so this is kind of contradictory for us. So for distance, this should be hold. The second thing is that positivity and self-similarity. So in other words, for positivity, we know that the distance between A and B should be greater than or equal to 0, and the D of A and B is 0 if and only if A is equal to B. Okay, and why? Because otherwise there will be different objects that we cannot tell apart. And the third and last property is triangle inequality. So for the distance, we should have D of A and B plus the distance of B and C should be greater than or equal to D of A and C. So why? Because otherwise one can say A is like B, B is like C, but A is not like C at all. So it doesn't make sense. So we need these properties for choosing distance to use a metric as a distance. Okay, so if we want to formalize the Kmeans algorithm, so we could write that we want to minimize over mu, minimize over clusters, sum over all clusters, sum over all points in the different clusters. We want to have minimum distance to the average of that cluster. So we could do this with we could break down this optimization into two different steps. The first step is that we fix mu and we optimize C. So we calculate the minimum of C that is equal to mean of C okay, and the second step is that we fix C and we optimize mu. So it means that we want to minimize over mu sum I from 0 to k for data points in clusters x minus mu I squared. So you could actually derive the optimal solution for this by taking partial derivative with respect to mu I, and you obtain that mu I is equal to 1 over the size of the cluster sum over the cluster points x. So this is actually the average point of the cluster points. So if we have something like this for this data, probably here is the mu I. One disadvantage of Kmeans is that Kmeans can get stuck in local optimum. So the initialization is important, and we have different kind of tricks to initialize the K-means differently to have a better clustering result. And sometimes K-means actually doesn't work as you expected. For example, in this kind of example, you probably want to have one cluster and two cluster, but K-means cannot cluster these points as you expect. So in this case, maybe you want to use another distance metric. In that case, K-means could work actually if you use K-means with another metric rather than Euclidean distance. Okay, so let's see an example in Scalar and how to use K-means in Scalar. Okay, so from Scalar, the cluster, we import K-means, we import numpy as np, we import seaborn to visualize the results, and we import pandas. Okay. Oops. Okay. So first we create some random points in here. So we use random (100) data points. And we just want to make sure, okay, now we have these data points in here. If we want to visualize this, we could use join plot. So this is the x of x component and y component. Okay, so we have something like this now, and we want to now apply K-means on these data points. So we first create K-means object is equal to K-means, and in here we set the number of clusters to 2, and now we take a look at the documentation to know. So as you could see here, to use that, we fit them on X. Okay. So now we have the labels in labels. Okay. So we don't need to actually use seaborn here because plot is so simple. So we use matplotlib. So we use matplotlib.pyplot. So we want to first select the cluster. So we could use we could select the first cluster points with x of K-means dot labels is equal to 0 and the x and y components. So in here now we could use the first cluster and we could use green for this, and for the second cluster we could use DC2. In here we have red and we have tilted show in here. Let's see what is the error. Okay, this is DC2. Okay, as you could see, this is the clustering results on the data points. So first we have this kind of data points that we don't know how could we group these together, but after the Kmeans, now we have some kind of labels to cluster the data points. Now actually you could, if you see the score in here, you could get the total score of your Kmeans, which is related to the Euclidean distance of the total points with your center. So let's see Kmeans score and print it. To print it, we could actually use it on the data points, so we could get the points. So sometimes maybe you have the question how we could choose the K in here. One method is to see the knee point in the score plot. So you maybe use a for loop. So for K in range maybe from 2 to 8, you want to see different cluster scores. So first I created scores, and in here I create the Kmeans object with K clusters. Then after that I use Kmeans.score, right? So on X, and I have to extend that to X because I want to visualize that. Okay, so now if I print the scores, I have something like this. Now I could plot the scores to, okay, now maybe to have more. Okay, now you could clearly see as you are growing your number of clusters, you have a better score or decrease in that some kind of loss function of your or distances of your cluster points, cluster centers, and the data points. So maybe for this problem, choosing 6 or some kind of knee points. This is the knee points, we use that in different methods. For example, if you remembered for PCA, we use something like this with variance, with explained variance to see that knee point. So in here you could use 5 or 6, or actually it is better to normalize them based on the maximum. So maybe scores divided by max of scores to actually, because it is negative and it is negative, so we have a positive in here. If you want that kind of plot, you could set the minus in here, but because it is a list, that is not possible. We could actually convert that to NumPy array. So NP the array of scores. In here we use np.max. Okay, now you could see we have in here we defined normalize the scores is equal to, and just note that when you use something like this, you should specify the axis. So in here the axis is 0 probably. And this is a funny thing that you should note that because those are negative, so you should use min in here. Okay, now we have something like normalized graph in here. Now again, we could use 5 or 6 to set your k for k-means. So I hope that you get the idea of how to set the k in k-means or k-nearest neighbors, or even PCA, t-SNE, and other methods that need some kind of hyperparameter tuning for number of clusters or a number of components in PCA and other algorithms. Okay, so I think, yeah, that's enough for this session. I hope that now you are able to group your data and cluster your data, and yeah, have a happy coding with that. See you in the next session. Bye.